Okay, so from the ideal gas law, PV equals NKT, if we let's say that we're thinking of T as being constant, but P and V can change, then if P is increasing, V must decrease such that the quantity on the right-hand side remains the same because T is not changing, and vice versa. So in the PV diagram, for a process where T is constant, in other words, an isothermal process, we have a decrease in P and an increase in V, and vice versa. The path in the PV diagram for an isothermal process, so that's an isothermal, is of that sort. And now we want to think of an adiabatic process and try to derive the path in the PV diagram for an adiabatic process. It won't be exactly the same, right? So we'll see, we want to try to derive this. So to do this, let's do first law, dE is equal to dQ minus dW. And for an adiabatic process, we have dQ is equal to 0, right? By definition, that's what that is. And therefore, dE is equal to minus dW. And so that is minus, we know what dW is, that's P dV, right? It's the infinitesimal work. So now let's do dE equals, so it's equal to minus P dV, but we can also think of this in terms of the change in temperature, right? So there's going to be a change in temperature, and we know that it's possible to get that change, dE, in terms of a process where the volume isn't changing, right? It just depends on the difference in the temperature, so I can write it like that. Of course, PV is equal to NKT, and so if I ask for the total change in this quantity, dPV, then I have P dV plus V dP, and that is equal to NK dt. But I can use this expression, these two expressions, to get rid of the temperature. So I can say that dt is equal to minus P over NCV dV, plug it into here and get a relationship. I'm trying to get a relationship between P and V to get a sense of how P and V change. What is the path in the PV diagram for an adiabatic process? So I have minus P over NCV dt. I'm going to put this into this expression and end up with P dV plus V dP is equal to minus NK over NCV P dV. Okay, so let's divide by PV, and we'll end up with dV over V plus dP over P being equal to minus NK over NCV dV over V. Well, we really want to put them on the same side, but let's just do dP over P is equal to minus, we'll end up, if we bring these two terms together and bring on this side, we have a minus this minus 1, so it's really minus 1 plus this term involving these constants, dV over V, So we can say the natural log of P is equal to minus 1 plus nk over ncv, the natural log of v, right? We integrate and we have some constant. And so we can say that P, right? So then we want to isolate the P, so we do the exponential. So we get P is equal to, right, so we have the exponential of this plus this, and that's the same thing as exponential of this times the exponential of that. And so we get, well, the exponential of this is just e to that, that's just a constant. So let's just call it, I don't know, a. E to the that is a, and then e to the this gives us v to the minus 1 plus nk over cv times n. But this is the same thing as 1 over v to the that, and so we can bring it to that side. So we end up with p times v to the 1 plus nk over ncv is equal to this constant. Okay, and so usually this quantity is referred to as gamma, 1 plus nk over ncv. And so we can write this as PV to this constant is equal to some, let's just call this a constant, is equal to a constant. And notice that this constant, these are just positive terms, this is greater than 1. And therefore we see that the behavior in the PV diagram is different from what we outlined for the isothermal process, right? The isothermal process has some value of P, then P is decreasing, V must be increasing, something like that. And because of this factor, it's greater than 1, we will be lower, right? So we'll have a curve that's lower. So this path is isothermal, and this path, so this is an isothermal path, this is an adiabatic path.